I know it's trivial, but I want to get that sorted out right now, because we're going to need, when you're manipulating matrices, it's not like scalars. You have to pay special attention, be very circumspect about dimensions as you go through it, or you can do silly things, make mistakes, and you quickly go wrong. So I point out this obvious thing with apologies to people who know it, because you have to keep an eye on dimensions before you do anything in matrix algebra. We're on time, so I'm going to get started. You should have a copy of the book in front of you. It's just like yesterday's book. It's really convenient that they're so confusing, because the only difference is the title on the first page. I apologize for that. Good to see you, man, anyway. So, obviously, it's yours to take away with, once again, and feel free to make notes on it or sell it on eBay or whatever you can get out, value you can get out of it. The same introduction as yesterday, so I'm going to gloss over the first few slides, and I want to get to this one, where we talked yesterday about the two distinct modeling paradigms that exist in systems theory. Yesterday, we spent our time talking about the input-output modeling paradigm. The distinguishing thing was that those systems had a single equation which connected the input to the output. If we were talking about the plant, the input I denoted as U and the output as Y, and we used the transfer function yesterday to capture the dynamics of those kinds of systems. Continuous time systems, we might use the Laplace transform with a complex variable denoted S. And in the last section yesterday, we spent time talking about discrete time systems, where, again, in the input-output paradigm, it's a single equation, but now using the complex variable Z. Now, that was what's sometimes called classical control theory, is based around the input-output paradigm. The other way of representing exactly the same kind of systems is using state space. And the bottom half of this slide shows the basic structure of state space equations. Again, you have an input, which is denoted U, and an output, which is denoted Y. But now there is a new set of variables denoted X. These are called states. They're internal to the system. And the fact that we've introduced an internal set of variables allows us to contract the high-order differential equation into a set of first-order differential equations, which is captured in the first of these two equations. So X dot is the first-order derivative of a vector X, representing the state variables. And the second of the two equations, so you can see X dot is a differential equation involving the input U and the state. First order, it's non-homogeneous, but it's a standard vector matrix differential equation. The second equation is purely algebraic. It connects the states and the input to the output. This equation pair is written in terms of t. The independent variable is time. So we can use this to describe systems in the time domain. One of the disadvantages you'll see shortly with using state space is that the link with the frequency domain is lost. We're working in the time domain today. If the systems were in discrete time, well, you're used now, because of the fourth section yesterday, to working with k as the independent variable, where k is the sample index. And so you recognize the first of these two equations is a first-order difference equation, and the second one is an algebraic equation, just as it is for continuous time systems. Now, just as for the input-output paradigm, you can transform from a continuous time to a discrete time set of equations. And when you do that in the state space paradigm, two of the matrices change. The notation I'm using is phi and gamma. These are Greek uppercase symbols in place of A and B. So when you see phi and gamma, you know immediately we're talking about discrete time systems. Another benefit, I don't know if you call this a benefit, but it's a feature of the state space paradigm, is that whereas yesterday it made sense, see, the discrete time theory is different, and it makes sense to separate that into a different module. So yesterday, section 4 focused on discrete time. For the first three sections, we're only working in continuous time. And that's because the theory is different. But for state space systems, the theory is so similar that it makes no sense to separate out the discrete time and the continuous time theory. There are one or two differences, but for the most part, the theory is the same. So I'm going to cover discrete time and continuous time systems in parallel today. there's no separation between the two. So, looking at the agenda, today's seminar breaks down into 4 sections, just as yesterday did, because the same timing constraints will apply. We've got breaks morning and afternoon and a lunch halfway through the day. So the day is going to divide into 4 1.5-hour sections. And the way I'm going to do this is that I'm going to spend the morning talking about the properties of systems described using the state space paradigm. We're not doing any control in the morning. That will come later on in the day. To begin with, I'm going to talk about state space systems. I'm going to introduce that method of description. I'm going to introduce things like eigenvalues and eigenvectors, which are fundamental to the description. Unless you can understand what they are and how to obtain them, you won't be able to go further. So it's important to understand that. I'm going to talk about different ways of obtaining the state equations. And then I'm going to show you the link between state equations and the transfer function, because you can obtain a transfer function from a state space description and vice versa. In the second section, I'm going to say that, right, we've already got our state space description, but what properties does it have? Now, yesterday we talked about stability quite a lot, and we probably think stability is quite an obvious thing. But when you've got a set of internal variables to play with, stability has a few permutations that were not there yesterday, and some of them are quite important. So I'm going to explain stability, and then I'm going to talk about 2 very important properties called controllability and observability. These capture, respectively, the ability that we have to control the internal states by manipulating the input, and to determine what the internal states are by just observing what's happening at the output. So these are fundamental properties when we come to design controllers, and later when we come to design estimators or observers. They're very important. So hopefully by lunchtime we'll have a very solid grounding in the theory of systems using the state space description. And in Chapter 7, we're going to use that theory to design feedback controllers. But we're going to design feedback controllers using the state vector, right? So whereas yesterday, you just hop back to this slide. Yesterday, we had a pretty simple thing conceptually. This was the system equation, and we wanted to design a feedback controller. What we did was we took the output and fed it back through a summing point to the input through a controller. What we were doing was using output feedback. Now, the concept with state feedback control is that you use not the output in the feedback loop, but you take the state vector, those set of variables which are internal to the system description, and you use them in a feedback loop. Now, there are several advantages that you get through doing that, mainly to do with the freedom that you have to choose what behavior the closed loop has. It's far greater flexibility using state feedback than it is using output feedback. So in Chapter 7, I'm going to explain how to use state feedback control. And there are several methods for doing it. They're reasonably straightforward if your system has one input. But when your system has more than one input, and these types of systems, you can easily cope with that. The processes get quite complicated. I'm going to show you a technique called eigenstructure assignment for use in those cases. I'm going to use a flight control example to show you that. It's quite an interesting tutorial that I've got set up for that. And then there are techniques to deal with steady state, which are a little bit different from what we did yesterday. Now, of course, if you're going to use the state vector in a feedback loop, I guess you better know what it is. I mean, it's not like the output. You can just connect a sensor on the thing and measure it. These are variables that are internal to the system, so somehow we need that state vector to use it in a feedback loop. And you have to somehow obtain it, and there is a way of obtaining it through an algorithm called an estimator or an observer. Those 2 terms mean the same thing. And in the 4th section, I'm going to describe the structure and design of linear state estimators which produce the state vector for use in the feedback loop. And so at the end of today, I hope to give you a fairly general grounding in the use of state space techniques for control. We'll be using the same the same tutorial as yesterday, the switching power converter. That will appear in several places today. So that DC-DC buck converter that we designed a phase lead compensator for, I'm going to reuse that to design the state feedback controller. And then there are two new tutorials. The first is a double mass system. It's a nice mechanical system that you could visualize how that would behave if you had one on the desk. Both of these first two systems have a single input and a single output, although we can change the output in the second case. So for the complicated systems that I need to have more than one input, more than one output, I'm going to adopt the flight control example, which you'll see is a lateral flight dynamics controller for a Vought F8 Crusader. I'll say more about that a little bit later. To remind you of the notation, the quad bullet indicates points which I think are really important, really pertinent to the material. Keywords are highlighted in that nondescript color, and I guess I'll reveal everything. We're dealing with matrices and vectors today, so you're going to see a lot of boldface notation like that. When you see boldface, it indicates that it's either a matrix or it's a vector. It's an array somehow of numbers that have a number of columns and a number of rows. So it's denoted by the integers which determine the size of those things. So the conformability constraints I mentioned earlier are important. Sometimes we'll see scalar quantities, so you will see the Times New Roman italic in there as well, but you'll be able to tell when it's scalar and when it's a vector quantity just by the font that's used. And lastly, whereas yesterday I tended to use prime notation for differentiation, in the literature for vectors, the dot notation is pretty universal, so we'll use dot notation today, whereas we used prime notation yesterday. That's pretty much the first introduction. Let's get going with the Chapter 5. The numbering obviously concatenates from yesterday, so we ended with Chapter 4 yesterday. We start with Chapter 5 today. I'm going to talk here about the state space paradigm. I introduce it in a fairly general way, and then we'll go on to determine two important properties of matrices, certain types of matrices anyway, eigenvalues and eigenvectors. It turns out that these are fundamental to the description, the state space description. The dynamics of the system are wrapped up in eigenvalues and eigenvectors. And then having determined what they are, we'll look at the dynamic response of the system, both its states and its output. And lastly, I'll show you this connection between the state space description and the transfer function description. If anybody doesn't have a manual, can you come up and pick one up, please? And while you're at it, maybe you can sign in. My pen has disappeared, but if you can grab a pen and use one to sign in, that would be appreciated. The quotation that's being used here is from Einstein, I suppose, famous guy. He said, nobody can visualize 4 dimensions. See, the thing is, we're going to work with vectors today, and just like in 2 dimensions, you can represent points in the plane as a vector of order 2. Well, there's no reason why vectors should be restricted to 2 dimensions or 3 dimensions. They can be of arbitrarily large size. And so conceptually, space represented by a vector can be arbitrarily large in dimension. I guess what Einstein's saying is that once you get beyond 3, that space is not something that you and I can visualize. Right? If this pointer represents a dimension in 3-dimensional space, a vector in 3-dimensional space, you can see how x, y, and z coordinates could determine its beginning and its end point. Well, what does a vector in a 4th-order vector look like with 4 elements? I mean, you can't visualize that, but mathematically it can exist. So I'm going to say a little bit more about that shortly. So let's recap. Yesterday then, we talked about the input-output paradigm. And I showed you a differential equation like this one, which connected the input, u, and the output, y, and higher derivatives of both through a set of constant coefficients, b's on the input side and the a's on the output side. And we saw that for systems where these coefficients were constant, this type of equation could be used to describe a system that was linear and time invariant. Linear because it is described by this equation, and time invariant because all of these coefficients are not dependent on time, they're constants. And for this somewhat unrealistic and very convenient set of equations, a single equation, we could apply the Laplace transform to determine how the system would behave in response to a set of, perhaps a different set of inputs, a different input. So the output of the equation in Laplace, y of s, would equal g of s times u of s. So there's the topics we used yesterday. And if we wanted to determine the frequency response of the system, well, we evaluated its transfer function for specific values of S. We used those on the complex, on the imaginary axis. Okay. Once again, if you're joining, there are books at the front here, and if you could sign in while you're picking one up, that would be great. Okay, the state space paradigm is different, and it's fundamentally different. In terms of the state space description, we still have the input denoted U and the output denoted Y, which might be scalar, right? They may just be single quantities, but I'm going to take a more general view that they may be vectors. So this is a representation of a system that might have an arbitrary number of inputs and an arbitrary number of outputs. Think, maybe there are 2 inputs and 7 outputs or something like that. But additionally, there is a set of internal variables called states, which will be denoted by a vector called X. I mean, that's the universal notation for the internal state vector. And so immediately you have 3 vectors which just describe the system and 3 dimensions of those vectors. Those dimensions are extremely important. I'm going to use the letters R, N, and M, to capture the number of elements in the input vector U of t, the state vector X of t, and the output vector Y of t, respectively. So, for example, a system which had 1 input, 7 states, and 3 outputs, the numbers R, N, and M would be 1, 7, and 3, respectively. These numbers fix the dimensions of the matrices in the state space description that's coming up. So when Einstein talked about multidimensional space, you can see already that he was working perhaps in terms of a system which might have more than 3 elements in its vectors. Okay. Now, in comparing these 2 paradigms, there are fundamental differences, and I want to perhaps introduce you. Because you see, what you could do is you could take this system and write it in either this way or in the state space paradigm. There's nothing to stop you doing that. The fact that it has 1 input and 1 output need not stop us. It just means that the input vector is scalar and the output vector is scalar. They both have 1 element, and the state vector has, well, how many does it have? It has n. It has the number of internal variables is equal to the order of the system. So you've got a system that could be written in either way. So why would you do one rather than the other? Well, the state space description has some advantages, the most important of which is that the dynamic equations are always exactly the same. You've got that pair of vector matrix equations which doesn't change no matter how complicated or how simple the system is. So once you're used to manipulating that same pair of equations, you can handle any system regardless of how complex it is. You can use it to model systems with more than 1 input and more than 1 output. We didn't cover techniques yesterday for doing that with transfer functions, although it is possible to use transfer function descriptions for multiple input, multiple output systems. But this you get it for free. Right? The ability to handle systems with many inputs and outputs comes for free with a state space paradigm. The theory is better suited to describing and handling nonlinear and time-varying systems, although neither falls within the scope of our seminar today. We can exploit the mathematics of linear algebra to describe these systems, and they are very convenient for computer solution. Computers are very good at doing repetitive tasks, and especially where you've got ordered structures of data in vectors and matrices. Computers are really good at handling that type of thing. This is boring, repetitive stuff, and there are software like MATLAB that will do that for us. To this list, I would also add the point that the theory for discrete time and continuous time systems is similar in the state space paradigm, and it's different in the input-output paradigm. So there are some benefits there. But we need to also account for the drawbacks, and there are a couple. The first is that the link with the frequency domain was rather simple before. Transfer function we just evaluated by replacing S by j omega. That is no longer there with the state space paradigm. We work in the time domain when we design systems this way. And the other one, I don't know if it's a drawback or not, but you do need to be conversant with matrix algebra and linear algebra as well. But by far the most important one is the first one, which is that you've got exactly the same set of equations. So it's the ability to capture the dynamics in a single set of equations, which gives this method its power. Yes. So when we had a transfer function description like this one, we were able to determine the frequency response for it by evaluating points on the imaginary axis, replacing S by j omega, and evaluating g of S, the transfer function, for all values of omega. That was very simple. Now we have a pair of equations. Let me go back and find that pair of equations, which I may not have written yet, which are differential equations in terms of time. Right? Now, how are we going to get to a frequency description from a pair of equations like this one? There is no straightforward way of doing it. The method would involve going to converting this into a transfer function description, which you can do, and then applying the techniques that we would from the input-output paradigm. The possible difficulty with that is that you may be dealing with systems that have multiple inputs and multiple outputs. So it's not a single frequency response that you'd have anymore, but you'd have many frequency responses, one for each of the elements in the transfer function matrix. So that's why I say that the link to the frequency domain is lost, because it's no longer a straightforward replacement of S with j omega. You've got you've got to transform into a transfer function description and then apply the S equals j omega rule. Yes. But you'd have to transform your state space description into a transfer matrix before you carried out that. What I'm talking about here is systems that are described in terms of this type of equation in the time domain. Yeah. Yeah, help yourself to a book. I'm sorry, those latecomers who don't have one. And if you could remember to sign in, please, that would be helpful as a sheet on the front. So these are the equations. There are two of them, and I want to introduce you to the terminology and the notation that's used when we deal with state space systems. There are two equations. The first one is a first-order non-homogeneous differential equation in X, the state vector, and it's called the state equation for obvious reasons. The second equation is an algebraic equation involving the state, which is the solution to the first equation, x of t, and the input, u of t. That is known as the output equation for obvious reasons. It delivers the output. The equations have three vectors and four matrices in them. And once again, we need to be careful about the dimensions. The vector x of t is the state vector. That's internal to the system description, and it has dimensions n by 1, n being the number of states. The vector u of t is the input matrix. It has dimensions r by 1, right? R rows, 1 column, so it has r elements in it. And the vector u of t is the output vector, which has m elements in it, so it's an m by 1 vector. The matrices A, B, C, and D have their own names. A is called the system matrix, and it's always square, because this has x dot has dimensions n by 1, and we are connecting an n by 1 matrix x of t through A to deliver an n by 1 matrix. So this must be n by n in dimension. The matrix B, well, that goes by two names. You could call it the driving matrix, or it's also called the input matrix. That must have dimensions n by r. It has to deliver an n by 1 vector, otherwise we wouldn't be able to add it to this to deliver an n by 1 vector. So it must have n rows, and it must have r columns to be conformable with an r by 1 vector. So the matrix B is n by r in dimension, and it's called input or the driving matrix. You can follow the same sort of logic to determine the dimensions of the C and D matrices. C matrix is called the output matrix, dimension n by n, and the D matrix is called the transmission matrix. It has dimensions n by r. Now, sometimes we want to write, we want a compact notation to represent a specific system, just like we wrote G of S for a transfer function. That was a nice way of capturing a single system description. But you've now got to represent this as four matrices. So sometimes what's done is that the matrices themselves contained within these curly brackets. And when you talk about an ABCD system, then that at least defines the system that you're talking about. So if you have more than one state space description, well, then at least you can identify the specific one by putting the matrices in the same curly brackets. Now, this is how you might draw the state and output equations. It's a form that you'll see many times today because we're going to use Simulink to model the behavior of these systems. And these are the two equations at the bottom. And you see that the state equation involves the matrices A and B. So in the diagram, it's this part of the diagram involving A and B. And so the dimensions I've written on the matrices as well as on the vectors that appear at different points here. And so the output equation, the algebraic equation, involves the matrices C and D, so it's this part of the diagram. Okay? So the way you look at a diagram like this is you say, okay, here's the state equation, x dot equals ax plus bu. Find x dot in the diagram, there it is. What does it equal? It equals a times x. Well, x must be the integral of x dot, so there's an integrator here, or more precisely, there are n parallel integrators in this block to deliver the state vector x of t. So x dot equals a times x of t, and this, of course, must be conformable, plus b times u of t. So then that part is the state equation. And let's just step through the dimensions of these vectors and matrices as we go. So I've told you A must be n by n. It's conformable with an n by n vector, n by 1 vector. Same conformability applies for b times u. And so what we're doing here is adding together two n by 1 vectors to deliver x dot of t, which is n by 1. You can check the conformability and the results of these matrix multiplications as I described earlier. Same thing applies for the output equation. Y is an n by 1 vector, so all the results of the two multiplications on the right must deliver two n by 1 vectors, and when we check the conformability, we find we do indeed have two n by 1 vectors which are being added together. When later we come to do Simulink simulation, this is what you'll see. I want to point out at this point that all of the systems that you come into contact with will have a state equation which looks like this. I mean, there may be different dimensions involved, and if we're talking about discrete time systems, then the notation may be slightly different, but they'll all look like this. However, the output equation is not always like this, and in particular, it's very often the case that the D matrix is 0. We'll find later that the systems which are converted from a transfer function description into state space form, it's always the case that the D matrix is 0, providing that your transfer function is strictly proper. Remember that meant we have more poles than we have zeros. That system is bound to have a D matrix which is 0. Systems which are proper, right, have the same number of poles as zeros, then you know that the state space description is going to have a non-zero D matrix. But I told you yesterday that proper systems in principle can't exist because of the infinite frequency behavior they have. So you very often find that you've just got a single C matrix in the output equation and no D matrix. Just for completeness, systems which are converted from an improper transfer function with more zeros than poles, they don't have a state space description. So you have to be converting with a proper or a strictly proper transfer function in order to get a state space description in the first place. Yeah. Yeah. Because yesterday, as you saw with a lot of those transformations we did in Chapter 4, a strictly proper transfer function resulted in a Z transfer function which was proper. There were the same number of poles and zeros, and therefore in the discrete domain, when we're dealing with discrete time systems, yeah, it's quite often the case that the D matrix is non-zero. Not always, but perhaps more frequently than with continuous time systems. Good point. Now, I wanted to try and connect this theory with something visual because a lot of what follows today is quite algebraic and mathematical, and there are fewer tools available today than there were yesterday to give you a visual impression of what's going on. see, yesterday we talked about frequency domain. We used the Bode plot and we used the Nyquist plot, and I could tell you geometrical features of both that were helpful. And for time domain systems, we exploited the transient response and we exploited the root locus plot. Again, you've got some nice graphical tools there that help you to visualize what's going on. But with this kind of system, described using the state space paradigm, you really don't have those kind of tools available to you. It's an algebraic description, and you have to be used to looking at vectors and matrices and extracting what you can from them. But I wanted to give you at least some kind of a visual description. So what I have here are the two system equations. By the way, I call these the state equation and the output equation. Collectively, they're called the system equations for obvious reasons. They describe the system. And so the first equation, the state equation, x dot equals ax plus bu, think of this for a second-order case with a two-input and a two-output construction. So this system has two inputs. So we might, for example, call these two inputs u1 and u2. They're scalars, but they're represented in a 2-by-1 vector u. So this point u of t0, that point there in this plane captures the value of the input vector at time t0. And as time evolves, so that point in the plane, u1, u2, it moves too because the input is changing. And so you have in this sort of three-dimensional graph a view of the evolution of the input over time. And of course, because the input's moving and the system is described by this equation, we could do the same thing if it were a second-order system with two states, draw the states in the plane, and then track the evolution of the state as a trajectory moving in this three-dimensional sort of graph. So now you have a link between the input and the state. And in the output equation, then we could do the same thing, which connects the first two graphs, the input and the state trajectories, to an output, and it's just a combination of the two through the matrices C and D. Now, there is a formal definition for the states, and reading it verbatim, the state is a minimum number of variables, very important minimum number, I'll tell you why in a second, whose knowledge at time t0, together with the input at t greater than 0, gives you the output at time t greater than t0. Now, the way to remember it, you need three things, right? You need to know the value of the state at time t0. You need to know the interval over which you're interested in looking, and you need to know what the input does over all that interval. And I'll show you why in a future slide. It's just in a few minutes. But those three things, the initial value of the state, the time interval, and how the input moves during that time interval. That's all you need. The system is described completely using these set of equations, just knowing those three things. Now, the thing about selecting the states, because with a system, right, you put it in the box and then you draw lines coming in and out. The inputs and the outputs are obvious. You know what they are. You know what inputs you've got available to manipulate the system, and you know what its outputs are. We may be dealing with sort of voltages and currents, and maybe there are mechanical things like force and movement, things like that. But the internal variables can be anything you like. You can choose what they are. It does not matter. They may or may not have physical significance. For example, you might choose things like voltages and currents if it's an electrical system, or you might choose things like, position or force or something for a mechanical system, but they don't have to be like that. They can be things like transcendental quantities, the cosine of force plus third tan of position or something like that. They can be transcendental and not necessarily physical quantities that you could measure. Some sets are easier to work with than others, but pretty much you can choose the states to be whatever you want. It does not matter. Well, it matters a little bit because some sets are easy to work with and others are just easier to derive in the first place. The only thing that's really important about the states that you choose is the number. That is unique. An nth order system must have exactly n states in the state vector. If it's a third order system, then x of t has three elements in it. It's a 3-by-1 vector. And A will be a 3-by-3 matrix. And all the other dimensions in the state space description are then fixed. If you don't get the number of states right, you will get into trouble. And I will show you in the tutorial shortly what kind of problems can happen if you get the wrong number of states. So obviously this system, you must have two states. If you had 3 states or 4 states in the description, things would go wrong when you started to control it. Yeah. Well, you have to know about the dynamics of the system in order to arrive at the state-space description. It's just the same as if you have a transfer function description. You have to model the system some way. You have to construct it, that's right. So if you are starting from a transfer function description and converting it into state space, you will know immediately. That's easy, right? But if you're not, if you're constructing the system from the start, well, you have to calculate what the order of the system is. Yeah, it'll come out in the model. Yeah. Now what I'm going to do is to show you an easy way of obtaining a state space description from a transfer function. And once you've seen this way, you'll find it easy for any strictly proper transfer function that you come across. This is a general transfer function of arbitrary order. It's one we saw yesterday, having n zeros and n poles. If it's a proper or strictly proper system, they're the only types I'm talking about today, because they're the only types that have state space descriptions. You know now that this is going to be an nth order system, and you know already that the state vector is going to be an n by 1 vector. So in this case, it's strictly proper. M is less than n, and I apologize for the typo. It's normalized so that a sub n is equal to 1. I adapted the slide from a second order example, and I forgot to change this. But the point is that the leading coefficient in the denominator polynomial is 1. That polynomial is said to be monic when that happens. A monic polynomial has a leading coefficient of 1. If it's not, divide through by whatever it is to make it 1. That's the constraint that you need in the first step. Now, the thing is that you don't have to remember much when you do this, but the thing you do have to remember is that when you follow this process, we define a variable called v, which is equal to u divided by the denominator, right? So you take the denominator of this transfer function, and that stays the denominator of v, and v is defined as u divided by a. Now, I'm fully aware when I teach this here that this whiteboard or flip chart is not going to be recorded, and so I apologize to those who are in the future going to listen to this. So let me just show you why I'm doing this. The transfer function, remember yesterday we defined it as the ratio of y divided by u, the output divided by the input in Laplace. And I also told you that it was the ratio of two polynomials, beta divided by alpha. Remember that? We called the numerator polynomial, involving all the coefficients on the input side of the differential equation, all the b's, that was beta of s, the notation used yesterday, and the denominator polynomial I called alpha of s. So what I'm doing here is I'm defining a new variable v as u divided by alpha, which in turn is the same, if you just follow this, as y divided by beta. Now, why would I do that? Well, the answer is that I can now write u as v times alpha, and I can write y, the output, as v times beta. I can express the input and the output now in terms of v, and that's the key to it, because now v can be an internal variable, and that's going to comprise the states in just a second. So when I step through this, you'll look at what I've just written, and it'll all be obvious. But remember the first step, you're defining v, whatever v of s is, as the ratio of u, the input, divided by the denominator polynomial. And therefore, what you can do is write it out. You can just multiply both sides by this v of s, and so, multiply both sides by alpha of s in the first equation that I've written here, and so you've got an equation for u of s, which is a polynomial now with v in it. All right, so that's the first equation, and that's this equation here. U equals v times alpha. And you could do the same thing from the output now, because you can express y of s as beta of s times v of s, and so now you have a polynomial with all the output coefficients with v in it. Now I'm going to take, firstly, an inverse Laplace transform term by term for zero initial conditions, and you know that every power of s that appears corresponds to a differentiation now, so s times v of s turns into v prime of t. I'm dealing with scalars, so I'll use prime notation firstly. And so now you have two differential equations here, one for u of t and one for y of t. Everybody with that so far? pretty straightforward so far. So all you have to remember on this slide really is how to define V of S. Everything else is just going to follow. Now here's the clever and unique thing about this method. We're now going to select states. State selection is an arbitrary process, so you can use anything you like. But there is one unique choice of states for a system like this, where the states are called phase variables. And the phase variable selection is this. I'm going to select x1, the first element in the state vector, as this variable v, the function of time from the previous equation. The second element in the state vector is the derivative of v, right, is v prime, and therefore it's related to the first element in the state vector by a differentiation. It's x1 dot. The third element will be v double prime, which will be x2 dot, and by the time I get up to the nth element, it'll be xn minus 1 dot. So now I've selected n states in here, and each state is related to the previous one through a derivative. This unique selection of states are called phase variables. It's important, and it's going to come back a couple of times. So now I've got to write the equation for the state, x dot equals ax plus bu. Now, x dot is the derivative of the state vector, and you can see what the state vector is already, x1 to xn, and I already have almost all of the state derivatives. I've got x1 to xn minus 1. All of those derivatives, we know what they are because they're derivatives of the states themselves. But I don't know x sub n minus 1 yet. All I have to do is go back to these original equations again and substitute the state variables into the two equations I've just written for y and u. So here we are. Here's u, and here's y. And what you'll find is that u contains the state derivative, the derivative of the nth state. The reason for that, just head back for a second, is that u contains v to the n, so the nth derivative of v is the first term in the u equation at the bottom. And so now it's a simple matter, almost. See, the output equation staring us in the face, you could write that down as a vector matrix equation immediately, but this one isn't quite there. I need to put this on the left-hand side so that I've got the derivative of the nth state, and so you end up with this equation for a derivative of the nth state, or you almost do because I made a mistake when I wrote it down. This term, the second term on the right-hand side, a sub n x dot n, that's a mistake, that shouldn't be there. So if you cross that term out, all the other terms there are present in the description of x dot, x sub n dot. So now we have everything, right? We've got the state equation that we need because we've defined the state vector and we know all the derivatives, and we already have this equation for y, which tells us what the output equation is, and you can really do the rest by inspection. The state equation and output equation look like this. Here's the derivative of the state vector. So this is x dot, and then the square n by n matrix is A. Here's the state vector, and here's the input vector over on the right, u of t multiplied by b. And then the output equation, well, that's obvious. It's just y equals c times x. And as I mentioned before, because the original transfer function was strictly proper, there is no D matrix. This is just a system with three matrices which describe it. Now, what's important is the structure of these different matrices, the A, the B, and the C matrices, because they have a unique structure in what is called phase variable canonical form. Phase variable because we chose the phase variables when we arrived at this description. First of all, the B matrix is really obvious. It has zeros in it except for the last element, which is a 1. The C matrix contains all the coefficients from the numerator of the transfer function, B0 to B sub n minus 1. Now, if n was smaller than n minus 1, you'd have some 0 elements in the C matrix, but let's assume that the relative degree was 1. Therefore, it's strictly proper with the largest number of zeros possible, then you'd have that number of elements in it. And n. It does have n elements. It's got to have n elements, otherwise you couldn't multiply it with an n-dimensional vector. So, yeah. So the number of outputs equals, oh, right, that's wrong too. That's wrong too. N equals 1 in this case. Thank you. I hadn't just noticed that. This particular case has 1 output. Thank you. Thank you. There you go. n doesn't equal 1, n equals... Sorry? I think it's a mistake because as I said, I've adapted this slide from something else, and I missed that point. Thanks for that. The other thing is that, so we know that the structure of the B and C matrices is unique. The structure of the A matrix is especially important. It's a very recognizable structure because the coefficients from the denominator all appear in the bottom row. All of the other elements in this matrix are 0 except for what are called the superdiagonal elements. You know that the diagonal elements of a matrix are like that. Well, if you just go up 1, that's the superdiagonal. And if you come down 1, that's the subdiagonal. So the superdiagonal elements are all 1, and that comes from the selection of the states as state variables, because x1 dot equals x2. x1 dot equals x2. So that's why we ended up with that superdiagonal being all 1s. Now, this particular form is sometimes called a phase variable canonical form. It goes by another name. It's called a controllable canonical form, one of the two fundamental forms that are used to transform transfer functions into the state space paradigm. And we'll find later that this special form has some unique properties that are very useful when it comes to control. I think I'm going to do a quick tutorial at this point based around the same buck converter that we used yesterday for the phase lead compensator thing. So we already know that this has a transfer function with 1, 0, and 2 poles in it, and we also know that those poles are complex conjugate poles. And so what you could do is just simply look at the transfer function for this, normalize the denominator, and then now you know what the A's and the B's are. Just plug them straight into the last two equations and see that you've got a phase variable canonical description for this system where the A matrix has the denominator coefficients in the bottom row. The superdiagonal now is just one element, so that's a 1 and the other element is 0. And then the B and the C matrices are exactly what you saw on the previous slide. So that then would represent a phase variable canonical description of this system. I'll do a quick tutorial in MATLAB just to introduce you to a couple of things. Excuse me a second. I'm rather struggling with this today. Here we go. Again, I'm using the cell-based programming approach. So this is divided into cells, and the first cell here does nothing more than we did yesterday, which is to construct the transfer function of this system using the TF script. So I'll run the first cell, and you'll see the transfer function appear in the workspace. So that's exactly the same as we had yesterday. Now, there is, although we haven't covered it yet, the state space description has, let's put these into the state space description first and go through it. This is just the matrix. This is the way you define matrices in MATLAB. So if we have an A matrix, which we have a 2 by 2 A matrix in this case, you use square brackets just like as if it was an array yesterday. Remember when we defined arrays like this array here, which holds the coefficient between these square brackets, that's an array of numbers. So the array holding A0, A1, A2, those numbers are just separated by white space. So it's the same with matrices. You write the elements of the rows separated by white space, and you demarcate the rows with a semicolon. So if we want to write a matrix which is 2 by 2 with the first row 0, 1, you write it like that, and the second row A0 over A2 minus A1 over A2. You write those two numbers like that. The reason that I'm dividing by A2 is to normalize the denominator, so A2 is 1. Effectively, that's what's happening here. Here's the B matrix. It's a 2 by 1 matrix. The first element is 0, then I need a semicolon to find the second row, and that's 1. C and D, and so we've got the four matrices, and I can now combine them into a state space description using the SS script. So SS, A, B, C, D, that creates an instance in the workspace of a state space representation of the system with those four matrices, and there they are, A, B, C, and D. Now, the transfer function, just off the top of the screen here, is second order, and therefore it has two poles. And you know already that those poles tell us about the transient response of the system. They're important in the description because they tell us about stability and transient response and other things. And there is a quantity called the eigenvalues, which is related to the system matrix. I'm going to cover it in just a second, which tell us exactly the same thing. And you get those from MATLAB by typing in eig of A. So the system matrix A has eigenvalues, and to find them, we're just going to type EIG. So the poles of the transfer function should be the same as the eigenvalues of the system matrix. When I run the next script, you can see that indeed they are. We have pole of the transfer function gives us 2 complex conjugate poles. Eig of the A matrix gives us exactly the same 2 complex conjugate numbers. Those things tell us the same thing. Now what I'm going to do is 2 things. I'm going to plot the step response of the state space system in MATLAB, and I'm going to plot the output of the state space system in MATLAB. Do those 2 things first. First of all, it's second order, so it's nice and easy to see this. This is the evolution of the internal states, x1 and x2, for a step input. We know that the output is oscillatory, so it's no surprise that the internal states are also oscillatory. And now if I plot the output of the state space system, see, all I did was, in this line here, I took the state space description and wrote step, and then this is the final value. So that's the final value of the x-axis over which the step response is plotted, 2.5 milliseconds. And that delivers these arrays, y, t, and x. So that's the output, the time vector, and the states. Okay, so first of all, I've plotted 2 states, x1 and x2 in 2 separate graphs. And now in the next cell, I'm going to plot the output, which is y. And that's, remember, from the state space description. And they look just the same as they did from the transfer function description yesterday. Now what I'm going to do is to write the same thing in Simulink. Now, if you haven't used Simulink before, it's a graphical tool for simulating the behavior of systems in the time domain. And it's very powerful when we're working with vectors and matrices, because it's kind of set up for that. So here is the ABCD system, the structure that I showed you in an earlier slide. Here's the derivative of the state, and then this block here represents however many integrators it needs to represent to integrate a vector of that dimension. So we have A times X plus B times U, and the U in this case is going to be a step input. Here's the D matrix, which we happen to know is 0, but MATLAB doesn't know that, Simulink doesn't know that yet. And then the output is C times X plus D times U. And then the output and the states, they're connected to these things, which just capture those variables in an array. So it's going to be an array of numbers of however many elements there are, because this is going to be a time vector output. And we're going to then pass these back into the workspace. Now, each of these triangles represents a multiplication. For example, the one at the top here is a D matrix multiplication. And it says, because it doesn't have to be a constant or anything, but this one says D, right? D is a variable that is in the workspace. So if I go back to the workspace and I look down here, I've already configured D. Okay, it happens to be 0, but C is not. Neither is B and neither is A. So those little triangles inside the Simulink model take those variables from the workspace, and when I run the model, it's just doing that multiplication and it's getting the dimensions right, hopefully. I'm going to tell you if the dimensions are wrong, but the dimensions will be right. Now, the notation that's used in the graphical way is that these thin lines which connect the elements together indicate that scalar quantities are being passed from one block to the next. But if we're dealing with vectors, what Simulink will do is it'll turn these various lines to very thick lines, which indicates that vectors are being passed. At the moment, it doesn't know because we haven't run it yet. But if I now run this simulation, what it'll do is run the step response for this and recognize which of these elements are vectors and which are not, and put the thick notation on there. So you can see immediately that there's a scalar input. D doesn't exist, so who cares, I guess. And there's one output. So this is a thin line over here coming out of the C multiplier. And the internal lines here, which contain the state vector, they're thick lines because we're dealing with n-dimensional vector in each case. So going back to the workspace now, we have 2 additional variables in there, one capturing the states and one capturing the outputs, and each of those is represented by 2,502 elements. There's a single output and there are 2 states. So these arrays are the right dimensions. So I can go back into the script now and plot those states against and outputs against time, which is all that's happening down here. So if I run the last script, what's going to happen is we're going to plot x1 and x2 in the same way as we did before, and we're going to plot the output on a separate graph just as we did before. So let's run this, and now what you can see is that I've got the first and the third. Let me take a look. So if you can see any difference between these, well, you're a better man than I am, because these are the same, right? I've plotted the output from the state space system in MATLAB over on the left. These are the two states, and I've done exactly the same thing from Simulink, and of course the results are the same. So I could do it directly as a script, or I could do it as a Simulink model. And if I do the same thing for the output, well, as you would expect, well, those graphs are the same too. Okay, so I'm just showing you now how you would enter matrices in MATLAB, how you would create a model using the SS script, and how you would do a graphical model in Simulink and import, and because you're exchanging data between the MATLAB workspace and the Simulink model, and that's a really powerful way to work. Okay, so let's clear all that out and close Simulink. Okay, I have a little bit of something a little bit different now, which we do need. This is more along the lines of matrix algebra or linear algebra. And I want to begin, because although these dimensions could be, these vectors can be arbitrarily large, it's very helpful if they're a second or third order, if there's 2 or 3 elements, because then you can connect the vectors with things you can imagine. For example, if you have a 3-element vector, you could think of it as something that captures a vector in 3-dimensional space, and we live in a 3-dimensional space, so it's reasonably easy to visualize this. Now, I'm going to explain how you would represent rotational movement using 3x3 matrices, and I'm going to use the terminology from flight control, from aircraft. Each of these represents a rotation of an element in 3-dimensional space, and we can think of it as moving coordinates. So what you have to imagine is that, imagine an aircraft traveling down the x1 vector, the way that these are drawn. And so if that aircraft were undergoing a yaw means that the aircraft's moving from side to side like that. It's a lateral motion. That represents a rotation about the z-axis, the vertical axis. In this case, I'm using the Greek symbol psi, PSI, like tip C. That's what that symbol means. So this rotational movement could be captured in a 3x3 matrix, which is this one. So if we had a vector and we wanted to change that vector by rotation about the z-axis, then you would multiply it by this one once you know what the angle is. Similarly, a pitch movement, okay, in an aircraft, you know that pitch means that you're going forward and the nose is going up and down. Pitch. That's a different 3x3 matrix. In this case, the pitch angle is theta. And then over here, there is a roll angle, and you obviously know what a roll angle is, and the angle is phi in this particular case. So these 3 Greek letters, psi, theta, and phi, capture the pitch, the roll, pitch, and pitch, roll, and yaw that's going on in the system. Now, of course, we might want to represent a movement which is a combination of all 3. All right, we might be flying through turbulence or something, and God help us. We might want to know that we're moving all 3 at the same time. Well, in which case, you multiply these 3 rotations together, and you arrive, for a fixed angle, at a separate matrix, which you might define as T. And so T can be thought of as a transformation from a vector at one point to a vector at a completely different point. It's a combination of 3 rotations. And as long as those angles don't change, you can just keep on using the same matrix to multiply the vector and always get the same answer. So you can think of a 3x3 matrix as a transformation. It moves a vector from one direction to another direction. That's what that matrix is actually doing. Okay? Now, it's used in various places in industry. I mean, in science and engineering, one place it comes up very commonly is motor control, but you may not realize that it was happening. This is a transformation that appears in what's called field-oriented control in motor control. People know what I'm talking about when I talk about the inverse part transform. Has anybody heard of that? There are no hands at all. Oh, there's one half hand, so a couple of hands. All right. So I feel sort of justified in explaining a little bit about the inverse Park transform. It's used in field-oriented motor control, where you attempt to position a flux vector inside the machine. And in the way that you work is that you calculate the position of the vector relative to the rotor inside the motor. So this machine has a permanent magnet inside the shaft, on the shaft of the motor, and the shaft is obviously spinning. So we're looking end on to the motor here in cross-section. So this is the motor shaft, which might turn in one direction or the other, and it has a permanent magnet on it. And we want to position that flux vector relative to where that rotor is. Of course, the rotor's turning with the machine, so that vector has to turn as well. And we represent the vector in terms of a pair of orthogonal coordinates in what's called the DQ axis frame. So the D and the Q, they're direct and torque directions for this vector. And this purple vector V might represent some vector that we want to represent in that coordinate frame. So that's how the information is passed into the inverse Park transform. And what the inverse Park transform does for us is it rewrites that vector information in terms of a coordinate frame that's referenced to these windings on the stator of the motor, because we somehow have to energize these windings to produce that vector. And it's no good expressing that vector in terms of something that's moving. You need it fixed relative to the stator windings. So you need to write it in terms of these alpha beta coordinates, and it's a coordinate transformation which is taking place. For example, here the difference between these two coordinates, orthogonal coordinate frames, is theta, and the matrix which performs this coordinate transformation involves sines and cosotrigonometrical terms inside this 2 by 2 matrix. So we're taking a vector expressed in terms of the DQ coordinates, multiplying it by a 2 by 2 matrix, and producing a 2 by 1 vector which contains information in the alpha beta coordinate frame. It happens it's very common in motor control. It produces a 2 coordinate vector, and the only other thing you need to do to that information is convert it somehow into a 3 coordinate system, because normally the motor is a 3-phase motor, and you need to know the information about how to energize each of the 3 phases. And that we do anyway through something called a space vector modulator. But this transformation, the inverse Park transform, is absolutely standard in motor control. It's very common in field-oriented control. And all we're doing is using a matrix multiplication to change one vector from one coordinate frame to another. Now, all these transformations are carried out by a square matrix. So what I'm getting at is that the square matrix has certain properties, and those properties are relevant to vector change. Now, there are 2 fundamental quantities which are very important to everything that follows. The first quantity is called eigenvectors, and for every n by n transformation matrix, you can almost scrub out transformation. For every n by n matrix, there are up to n vectors whose direction doesn't change when you multiply the vector by that matrix. So imagine that you've got some kind of a vector in 3-dimensional space. Perhaps this pointer represents that vector. You multiply it by a transformation matrix to change that vector to a different direction. So almost every vector that you can think of is going to have a different direction after the matrix multiplication, except for up to 3. There are 3 vectors which won't change. There might be less than 3, but there'll be up to 3 vectors who won't change. And those unique vectors, they're unique to that particular transformation. They're called eigenvectors. Now, the thing is that if you can find those eigenvectors, under the transformation, they will be unchanged in direction, but their length might be changed. You might have a different length after you've multiplied it. So associated with each eigenvector is an eigenvalue. So each n by n transformation has up to n eigenvectors and n eigenvalues. Each eigenvalue is associated with an eigenvector. They play a fundamental role in the behavior of dynamical systems. Now, it would be wonderful if you could say that because you have a 3 by 3 matrix, you've got 3 eigenvectors and 3 eigenvalues. And unfortunately, you can't say that, because you only know you get up to 3 eigenvectors. You don't know that you get 3. You'll get 1, you may get 2, you may get 3, but you don't always get 3. matrices which have this unfortunate property are called degenerate matrices, and they lead to problems when you come to describe the system. So an n by n matrix always has n eigenvalues, but it might not have n eigenvectors. Matrices are called degenerate, and the degeneracy is the difference between n and the number of eigenvectors that you get. So here's a graphical way of thinking about an eigenvector. This purple line, this called crimson line here, represents a vector which is unchanged under the transformation using an n by n matrix A. So A is going to be 3 by 3 because it's a three-dimensional system. So W sub I, whatever I is, 1, 2, or 3, under multiplication by A, that vector has exactly the same direction, but its length in this case is increased by the quantity lambda. So the original vector had coordinates A, B, and C in the x, y, and z directions, and after you've multiplied it by this, its length has changed, so its coordinates are going to be lambda I times A, lambda I times B, lambda I times C. That lambda A is the amount by which this vector has increased in length. So the eigenvector is Wi, and the eigenvalue that's associated with it is lambda I. You can write the same thing in vector matrix notation as A omega I equals lambda I omega I. Now, unfortunately, it's not quite as simple as that, because eigenvalues, as well as the elements in the eigenvector, can be complex. They don't necessarily have to be real. So I'm giving you a visual representation of something that is applicable only if we're dealing with real eigenvalues and real elements in the eigenvectors. It's not necessarily like this, but I'm trying to give you a visual way to think of eigenvectors and eigenvalues. So the eigenvalues then are scalar, always, so we don't use boldface for them, but they may be complex. The eigenvectors are vectors which themselves may have complex elements in them. And we would like to find what these are, because you'll see later they come into pretty much everything that follows. Now, the eigenvalues are reasonably easy to find, and you always find these first. They're found from evaluating the determinant lambda I minus A. Now, you leave lambda as a free parameter when you calculate this, and I is an n by n identity matrix. So you know what an identity matrix is now. So you've got two n by n matrices, you can do the subtraction and then calculate the solution to that. And the solution will be an nth order polynomial in lambda, because lambda is the free parameter that you left in that equation. So here it is, it's lambda sub n, right, in that term, and then all the others have some coefficients associated with them. And like all polynomials, you can factorize this to reveal what the roots of that are, roots of this are, and they're lambda 1, lambda 2, up to lambda n. So this then is the polynomial which captures the n eigenvalues of the system. And these eigenvalues, if we've started with a transfer function description, actually turn out to be the poles of the transfer function. So this is the characteristic equation of the transfer function that we started with. It's just that we're looking at lambda as the independent variable, not s. It's the same equation. So the coefficients are the same, and therefore the eigenvalues are the same as the poles. Now, there's two easy ways of checking whether you found the right eigenvalues or not, and they rely on you finding the product. Right, so let's say you found what lambda 1 and lambda 2 and all the way up to lambda n are, but you're not sure that they're right. The easy way to check is calculate the determinant of A, and the determinant of A should equal the product of all the eigenvalues that you found. So if you found eigenvalues 1, 2, and 3, well, hopefully the determinant of A is 6, hopefully. If it's not, then you've made a mistake somewhere. The other way is you calculate the trace of A, and the trace of A should be equal to the sum of all the eigenvalues. So if you find eigenvalues 1, 2, and 3, the sum is 6, and hopefully the trace of A will be 6 as well. Do you remember what the trace was? The sum of all the elements along the leading diagonal is the trace of a square matrix. So you sum them all up in A, that's the sum of all the eigenvalues. Now, the way I've written this, I've used m sub I here, because it's possible, just like the poles of the system can be repeated, right? You can have, for an nth order system, you must have n poles, and similarly, you must have n eigenvalues, but they might not all be different. Some of them might be the same. If you've got two or more the same, then that particular pole or eigenvalue is said to have a multiplicity of 2, 3, or 4, whatever it happens to be. So you have to remember that you might have multiple repeated eigenvalues when you do this, and take that into account, which is what the m sub I means in those two equations. So those are the eigenvalues. You typically find those first because you need the information to calculate the eigenvectors. The eigenvectors are found by solving this equation, a minus lambda I times I. Now, you know what lambda I is, so you've now got n of these equations to solve, and you're looking for solutions to it. Now, there is a pretty obvious solution to this equation, a minus lambda I times wi equals 0. If wi is 0, then you found a solution to it. That one's not allowed. That's called a trivial solution. And you're looking for non-trivial solutions, meaning you're not allowed to make wi 0 to this equation. A vector which satisfies this is said to belong to the null space of a minus lambda I. And there's a nice little script in MATLAB called null, which I'll show you in a moment, which allows you to calculate these eigenvectors. So you found the eigenvalues. You're definitely going to get n eigenvalues, and you hopefully are going to get n eigenvectors, but you might not. Depends on your luck. Find the eigenvalues first, then use the information to find the eigenvectors. Now, when you write down your eigenvectors, usual practice is to normalize them so that their length is 1. Direction won't change just because you change the size of the elements in it necessarily. Here, for example, is an eigenvalue that someone's found, minus 1, 0.5456, 0.5981. And if you calculate what the 2 norm of this is, so you square each of these elements, add them together, and take the square root, that tells you the length of that vector in what's called the 2 norm. And what you do is you divide each of the elements by that length. Well, the length of it happens to be 1.2866. That's how long that vector is. Three-dimensional vector, so you can imagine how long it is in three-dimensional space, 1.2866. And then what you do is you divide each of the elements by 1.2866, and you write it in this form over here. That means that it's been normalized. Some of the computations that we're doing later on require the eigenvectors to be normalized so that their length is 1, and that's how you do it. Okay. And I want to give you some examples of eigenvectors in ways that you can perhaps imagine. And so I'm choosing 4 examples of eigenvectors for transformations in the plane. The first one is unequal scaling. Unequal scaling is pretty recognizable because the matrix which does that is a diagonal one, and its diagonal contains 2 different numbers. So, for example, expressed in the plane, where we've got an orthogonal set of coordinates, x1, x2, this kind of scaling would change vector v1 from this direction, v1, to this direction, but also its length is different. All right. So if you draw a rectangle around v1 and a rectangle around v2, it's the size and the length and the height of that rectangle will be different under the unequal scaling. So try and think of vectors that wouldn't change their direction under that kind of thing. Well, there are only 2, right? There's this one, w2, and this one, w1. Doesn't matter what you do to them. Their length might be different under this, but their direction certainly won't be. So there are 2 eigenvectors here, 1, 0 and 0, 1 expressed in this orthogonal coordinate scheme. That's unequal scaling. Now, if k1 and k2 are the same, you've got equal scaling, which means it doesn't really matter which vector you start with. Its direction isn't going to change. You just changed its length. And in this case, well, where are the eigenvectors for this? It's certainly true that x1 and x2 are going to be eigenvectors, but so is every other vector in the plane. And so what you normally do is you select 2 orthogonal ones. Because the one thing about eigenvectors is they're orthogonal. They point away from one another. And so you'd normally pick these 2, but you can pick any 2 you like. This is an example of a type of matrix that's like that. How about a rotation? This happens to be the inverse part transform that we looked at earlier, and it represents a rotation in the plane. One vector, v1, under this transformation is rotated through an angle theta. So which 2 vectors are unchanged in direction after this? Well, the answer is none of them in the plane at all. The eigenvectors are complex in this place. In this case, I don't know how to draw complex vectors on a PowerPoint, so you'll have to trust me that they are complex. And the 4th example is called a shear example. So imagine that this first rectangle drawn to the corner of V1 is a block of rubber or something, and you push the top edge of it so that it's kind of in shear, V2 obviously has a different direction now under V1, so you've got this kind of parallelogram thing going on. And obviously W1, the vector along the x1 axis, is unchanged in direction under a shear, but certainly it's not true that x2 is unchanged in direction, because that's kind of pushed that way. So x2 is no longer an eigenvector. There aren't any others. This is an example of a transformation matrix which has only one eigenvector, but it has two eigenvalues associated with it. It's called a degenerate matrix. And let's take an example and just prove to you why that's the case. So if we have an example, where are its eigenvalues, right? So its eigenvalues are going to be at the solutions to lambda I minus A equals 0, and it's a scalar quantity there. So what you're going to have here is the matrix that we're going to take the determinant of is going to be lambda minus 1 minus K, 0, and lambda minus 1, and it's a determinant we want of that. Well, what is it? It's going to be lambda minus 1 all squared equals 0. So you've got two equal eigenvalues. Two equal eigenvalues means that you might get one or two eigenvectors associated with them, because you only get degeneracy when you've got repeated eigenvalues. And this one obviously has repeated eigenvalues associated with it. So unfortunately, we've lost one of the eigenvectors. Okay, I was supposed to do a tutorial at that point, but I'm going to skip over it. It's a trivial one. I want to talk now about the state response and how you compute it in the time domain. And I want to remind you first how you would treat a first-order homogeneous differential equation if you wanted to solve it. The most straightforward way is through a method called separation of the variables. So here's a first-order ordinary differential equation. There are no partial derivatives, and there is no other terms apart from x, so it's homogeneous. And so what you would try to do is to separate x onto one side and t onto the other. So you divide both sides by x and multiply both sides by dt. And so now you have an equation where these two variables are separated. And we can now integrate the left-hand side, that's a logarithm, and the right-hand side where it just contains a constant, but we're going to integrate a constant, and we're going to choose two limits of integration I'm going to call t0 and t. So we can now evaluate this. Well, the constant a just can be taken out, and you end up with the difference between t and t0 on the right-hand side. And then you have the difference between the ratio of two logarithms, if you like, to form the left-hand side. And so what you can do is to take exponentials now to get rid of that nasty logarithm, and take x of t0 over onto the right-hand side, so this is what you end up with. By the way, sometimes the notation gets a little bit confusing. A is a constant, and you have to remember that. So this is not a as a function of time, it's a multiplied by the difference between t and t0. And for that reason, sometimes when people write this out, they put the a on the other side of the bracket just to make it obvious that we're not dealing with a function of time. But I'm going to leave it this way because it's the way I'm used to. So what you have is pretty much what you expect for a first-order differential equation. It's a solution which involves an exponential, and that exponential has a in the exponent. Now, when you deal with vector equations, absolutely nothing changes. It's just that you have to realize that you're dealing with vectors and matrices rather than scalar quantities. And the solution to the equation x dot equals a times x, where a is a matrix, so this is the homogeneous part of the state equation, is simply e to the a times t minus t0, providing a is time invariant, times x of t0. So you have now a solution to the homogeneous equation. It's the complementary function from yesterday, because it does not take into account the input. The only thing is you've got to compute a matrix exponential, and I don't think the way that you do that was in the notes from yesterday, but there's a really easy way which involves a power series in A, and you just keep going with this. Take powers of A times t to the power over whatever the power is factorial, and you just take as many terms as you need to get the precision you need. So this is the series solution for a matrix exponential. Now that's only half the problem, because we've solved the homogeneous state equation, but you know that there is ax plus b times u, and so we need to solve the non-homogeneous part as well. And so what we do is the same as if it was scalar. We assume a solution and then plug that back in and see if it fits. And the solution that we assume is e to the at, because that's what we've just found for the homogeneous part, times some unknown function, c of t. So we don't know what that function is yet, but let's assume that there is one. Now, if we're going to have this as a solution, it better complies with the first equation here, so let's see if it does. We'll differentiate it. It's a product of two functions, so we need the product rule for differentiation. So first of all, we'll differentiate e to the at, that gives us a times e to the at, leave the second part unchanged, and then add in the first part times c dot of t. So that's this solution differentiated on the left-hand side. And on the right-hand side, we'll just plug the solution into where x of t is, and you end up with a times e to the at times c of t plus this input, b times u of t. And you can recognize now that terms will cancel. This first term on each side can be cancelled out. And so you end up with c dot of t, right? Take this term over on the other side, equals e to the minus at, because you've taken the exponent onto the other side, e to the minus at times b times u of t. That's what c dot of t is. And so we need to integrate it to find c of t. And now we have what we think is that function. So now let's plug that back into x of t and see if that's a solution. Well, it is a solution, providing that e to the at is taken to the other side. So you end up with e to the minus at on this side, and that's brought inside the integral to this. So this is the solution to the non-homogeneous part. This then becomes the particular integral, or the steady state part of the solution. So just yesterday, when we talked about transient and steady state parts, or free and forced parts, or complementary functions and particular integrals, are all the same thing. This is the particular integral, and the total solution is this plus the original solution in the previous slide to the homogeneous part is that. Right. Now, remember when we defined the states, and I told you needed three things. You need x of t0, you need the interval over which you're working, and you need u between t and t0. Those are exactly the quantities that you need in order to solve this equation, don't you? You need to know what x of t0 is. You know a and b already. You need to know what x of t0 is. You need to know the interval over which you're going to compute the result between t and t0. And you need to know u in that interval, u of tau, because tau is the dummy variable of integration. So providing you know those three things, you can solve this and obtain the state. And providing you know what the state is, the output is simply an algebraic combination of this and u of t over that same interval. So you can find the output simply by plugging in that solution. There it is. So there is a reason why you need those three quantities to define the state, and you define the state that way because you need them to define the dynamic response of the system. Now I'm going to talk about discrete time systems next. And I think what you'll see is that the theory mirrors very closely that of the continuous time system. And in fact, there are no differences in the first two sections today. The differences will become apparent when we come to design closed-loop systems. So the only thing that's different, well, I suppose there are three things that are different in the state equation pair. The first is that we're dealing with sample systems now, so the independent variable is the sample index, not continuous time. The second is that the system matrix has changed from A to C, and the third is that the input matrix, or the driving matrix, has changed from B to gamma. For an nth order system with the same number of inputs and outputs, the dimensions of these matrices don't change. So I've put the dimensions on. If you take the previous diagram that I showed you and just change the notation, you'll find it's the same diagram, except that the integrator is now replaced by delay elements in here, because the state vector now is delayed by one sample interval relative to x of k plus 1, so it's not an integration that's taking place, or it's not n parallel integrations, it's now n parallel delays. So you've got zeta minus 1 times I, and writing I sub n this way means that you put a dimension on the identity matrix, so you can see it's an n by n matrix by writing it that way. So the dimensions are the same, and if you wanted to capture this in a nice compact notation, you use phi gamma CD between curly brackets, and it means the same as ABCD. And the other difference is that you've got delay elements rather than integrators. So let's see how we get from a continuous time to a state space representation. The solution to the state vector then needs to be this. X kt plus t must satisfy the solution that I've just given you to the state equation. So you've got e to the at times x at the beginning of the sample period, which is kt. And then you've got the same integral as we have before, but you're integrating over one sample period between kt and kt plus t. A simple change of variable inside the integral gets you to this. So we're not doing anything but changing the variable now. Now, when we are doing this, we are assuming that a zero-order hold is applied between the input at time t and the input at time t plus kt, so that the input is static over that period, right? And therefore, u is not variable. It's a constant, and it can come outside the integration. And b is also constant because it's a linear time invariant system. That can come out as well. Don't be tempted to take these out on the left of the integral, because otherwise you violate the conformability requirements of vectors and matrices. This integral must give you an n by 1 vector result, otherwise it can't be added to the first term to produce the term on the left. So when you calculate the dimensions of this, e to the a times something, that is going to be an n by n matrix. B, we already know, is m by r. It has m columns and r rows. The number of states determines the number of rows, and the number of inputs determines the number of columns. So you've got n by n, n by r, r by 1. And when you do that, well, the result is n by 1. So you have to factor these out on the right of the integral. Now, the thing is that because this is a constant in here, e to the a times something, it's going to turn out to be a constant. Because we're using a zero-order hold, you can say that this term, e to the at, is a constant, and so is the integral. And you can treat those as separate matrices. So what we do is define phi, this matrix, as e to the a times t. That becomes phi times x of kt. And then whatever this integral is here, between 0 and t, e to the a, so e to the a times eta by the eta, times b. Right, so b is included in that definition. That becomes gamma, and that's your new input matrix or driving matrix for the discrete time case. You won't ever need to do this, but this is where these matrices come from and why they're different from the continuous time case. MATLAB will take all the hard work out of this for us. Now, we've now got a difference equation, a first-order difference equation, and it's reasonably easy to just tabulate the evolution of that difference equation as against sample interval. So at time t equals 0, we'll assume the input is 0 at that time, and you've simply got x of 0, whatever that happens to be. Time t equals 1, now you can plug x of 0 into this. So when k is 1, when k is 1, you've got yeah, okay. So I suppose this should be the left hand. It should be k plus 1, I guess, down here. So this is 1. You've got phi times x of 0 plus gamma times u of 0. And then when it's 2, the next sample interval in, you've got the next sample, the next state vector equals phi times the previous state vector, which you've just computed. It's that one. So it's phi times the previous state vector plus gamma times the new input. And then you keep going. The next time around, you've got x of 3 equals phi times x of 2, which you just computed, and that's getting longer inside these brackets, plus gamma times u of 2. And when you've done this a boringly large amount of times, you recognize that a pattern is emerging in here, because the fact that you've got phis which just keep multiplying up mean that you've got the first term is always x of 0, and that becomes multiplied by whatever power of phi you happen to be on that sample interval. So there's that part of it, and then the rest is a summation involving products of gamma, phi, and the input, and that is the solution. I mean, it's a tedious exercise to go through it because you've got lots of brackets and expanding going on, but that's the solution to the discrete time state equation, which then can be just plugged straight into the output equation to give you the discrete time output equation in closed form like that. Let's do a quick tutorial. So I'm on 5.3. All I'm going to do is plot the state response of the system in tutorial 5.1. That was the buck converter, and I'm going to use the step invariant method to obtain a discrete time equivalent of that. The step invariant method is the one that we use, called the zero-order hold equivalent method, and we'll examine its state trajectory. It's not a very difficult thing to do in MATLAB, so let me show you how we would do that. First of all, we're going to create the state space representation, as we did in the previous slide, for that switching converter. This, I ask you to trust me, is what we ended up with. And we'll plot its step response just as we did before, over a 2 millisecond interval, and record the results and then plot them. So this is the step response. Seen it several times. And what I'm going to do now is plot these states. And the states plotted on the same graph, as if x1 and x2 are the different axes, and this is the step response. So initially we had a 0 input. The state was here because both x1 and x2 were 0. And then we input a step input, which will force the thing to a different steady state. Well, it's oscillatory, so what happens is these sort of states sort of interact with one another to produce what looks like a nice kind of spiral that's going on. And what I could do is represent that information in this three-dimensional form, in which time is the sort of axis that's going along in this kind of direction. So this is time between 0 and 2 milliseconds, and then the x1 and the x2 axes, they're the plane. That's the sort of backboard over here. So you see that the state is evolving in that way. And I guess if I were to tilt this so we look end on, it is indeed the spiral. It's just that the x2 axis is the vertical axis and x1 is horizontal, and I had it the other way around for the previous diagram. So if you wanted to, you could represent the information in that way too. Sometimes that's helpful. And then finally what we're going to do is to discretize this and show the same kind of information again. Now remember, yesterday we used the C to D script in MATLAB, which converted a continuous to a discrete transfer function representation. Nothing to stop us doing that with a state space representation as well. And when we do it, be sure to use the zero-order hold method, because that is the way that things are done here. I'm going to use the same sample frequency that we used yesterday, and inside the workspace in a moment you'll see that we get a different set of matrices, phi, gamma, C, and D. Now these are the state space matrices. It's a physical system, so we typically have a strictly proper transfer function, which in the end gives us a D matrix, which is 0. You can see at the bottom of the screen. And we'll plot now the output of this. Now, when I'm plotting the output, it's the same thing as before. I've got y, t, and x. These are the arrays which are going to be created to hold the output, the time vector, and the state vectors. And I'm doing step, GSSD, that's the system that's been created through wherever it is, SS in the previous screen, and the time. But the difference is that when I plot the response here, I'm not using plot command anymore. I'm using stairs, because this is a discrete time system, so it's going to have values at particular intervals of time. Rather than joining them with a smooth curve, we know it's discrete, so it's kind of better to represent them as a sort of staircase diagram. So you use stairs instead of plot, and when you run this script, you'll find that it looks very, very similar to the continuous time case, but if you were to zoom in on perhaps a part of this, let's pick one random peak, you'll find that it is in fact a steppy thing because it's a discrete time system. So stairs does that for you, whereas plot does not. And I suppose you could go through the same exercise as before, representing this in any of those forms. This is what happens if you look down onto the phase plane, what's called the phase plane of it. You can see the steppiness when you're away from, you're at 45 degrees to the coordinates. So that's how you represent it. It doesn't matter whether it's continuous time or discrete time. You can manipulate it in the same way. Okay. Now, before I go on, I want to talk a little bit about autonomous response, and the next section is going to talk about a topic called phase portraits, which are only relevant to second-order systems. We won't be using them later on. They are useful background information if later you come to study nonlinear systems, so I want to introduce them from that aspect. But I also think that phase portraits give us a helpful insight into the behavior of dynamic systems in general. So even though we won't be using this information later, I think it's helpful to present it. It's based around a homogeneous response of the state equation. So this is the homogeneous response, no input. And we can examine the solution to the equation because it's going to have interesting dynamics based on the initial condition. This is what the initial condition response will be. It'll be two separate equations where the eigenvalues play a fundamental role. Now, if the initial condition is here, x at t0 on the plane, it's going to evolve over time as we just let it go. You think about some dynamic system that you displace from its equilibrium position and just let it go. Right? That's an initial condition response because there's no input to the system. It's just going to go twanging about until eventually it reaches an equilibrium point. And so over some interval of time between t0 and t0 and t1, the trajectory does what's shown here in this three-dimensional graph. And if you turn this so you're looking down the time axis, well, you might get some kind of thing like this. Now, if you were to choose a different initial condition, then x of t0 will be a different point in this x1, x2 plane. And if you carried out the same test, you get a different trajectory. Yeah, so the t-axis comes out here.
Right, and that's why the graph would be just a blue line straight up and down.
No, well, I mean, there's a limit to what I can do with PowerPoint, right? But here you can see the time. The vector x1 is over to the right down here. So at time 0 it's there, and here it's going the other way. Yeah, PowerPoint's not the most user-friendly tool to use. I'm trying. You're absolutely right, but I do what I can. Anyway, the point I'm making is that if you had a different initial condition, you'd have a different trajectory. And if you got very obsessive about this and you picked 100 different initial conditions and you plotted the way that they behaved, well, then you'd have a unique set of patterns. And these are called portraits. They're called phase portraits if you've chosen the x1 and x2 using the phase variable approach, where x2 is the derivative of x1 or vice versa. Then you've got a specific portrait called a phase portrait. And it turns out that for stable and unstable, for linear time invariant systems, the patterns that emerge when you do this exercise fall into one of 6 categories. The names that are applied here refer to the category of the equilibrium point, which for a linear system is always the origin. The patterns fall into the categories stable node, stable focus, center. These are the 3 stable categories. And there are 3 unstable categories: unstable node, unstable focus, and saddle point. This diagram appears in your books, and it's the best that I could do with PowerPoint, but I'm going to refer to the next slide, which conveys the same information, but is more beautiful to look at. There's no other reason. Now, what I did was I did this in MATLAB for different systems, and you can see, because of the starting points of each of these trajectories, the array that I've used between plus or minus 5 along the x and the y directions. Each starting point of each line indicates an initial condition, and then I just color-coded them, and of course they're uniformly gray in your books, but I color-coded them on the slide, and you can see that for a system which has 2 real and stable eigenvalues, remember eigenvalues and poles are the same thing, then you end up with an equilibrium point called a stable node, because all of these trajectories make a nice, smooth, kind of combined exponential thing, and you can pick out a straight line going through the origin there. So there's no kind of swirliness going on with this nice approach, with this nice situation. -1 and -2 are real, stable eigenvalues, and you always get a pattern like this called a stable node. Now, if you had complex conjugate poles or complex conjugate eigenvalues, and they were stable, you get a similarly stable response, but now it wouldn't just follow a line in there. What would happen is that because of the oscillatory effects that are introduced, this looks like a little bit of a vortex that's happening in the middle, so you get a swirliness that's going on, and these eigenvalues are not very complex, plus or minus 1 plus or minus I. If you had a much bigger imaginary part to the eigenvalues, then this swirliness really gets out of hand. You end up with something like we saw in the previous slide, the previous MATLAB plot. It gets like a real sort of vortex going on there, but you can recognize the stable focus and how it's different from a stable node. Now, the equilibrium point is a center when you have purely imaginary eigenvalues, and you know that systems with purely imaginary eigenvalues oscillate indefinitely. The oscillations go on forever and ever and ever. And that's reflected too in what you end up with, which is a series of oscillations, the magnitude of which depends on the initial condition. If you displace it further, then the oscillation goes on with a larger amplitude. If there's a small initial displacement, then the oscillation is smaller. So you end up with this kind of rings of Saturn effect where you've got center, the equilibrium point is called the center. Now, for unstable eigenvalues, you get the same kind of plot, but they're unstable, I guess. An unstable node consists of real eigenvalues, just like the stable node did, but at least one of them lies in the right half plane. In this case, both of them do. I'm sorry, they both lie in the right half plane. That's the unstable node thing. And you can recognize it's unstable only because of the axes. Right? So clearly we've got a situation where the trajectories are unbounded as time becomes infinite. The unstable focus means that you have a pair of complex conjugate eigenvalues, both of which are in the right half plane, and so the swirly effect goes on because there's oscillation involved, but the amplitude is increasing indefinitely. And lastly, the situation where you've got two real eigenvalues, but one of them is stable and the other one is unstable, gives rise to what's called a saddle point. That is the name of the equilibrium point. It's a saddle point because what happens is the trajectories begin with the best of intentions by going towards the equilibrium point, and then they change their mind and they go off to infinity in a different direction. So they kind of get sucked in towards it in one direction and repelled away from it in another. So it's a saddle point, right, and you've got this kind of pattern. Now, the significance to the type of systems that we're talking about is that yesterday I explained how classical second-order systems can be written in a transfer function form with two variables called damping ratio and the undamped natural frequency. We called these zeta and omega n, respectively. And I also showed you that the shape of the transient response depended on zeta alone, and therefore I thought it would be interesting, and it is interesting, to look at the evolution of the initial condition as we change zeta. Now on the left, I've got the autonomous response presented in the same sort of phase plane format, but the initial condition now stays the same. It's at 1, x2 is 1 and 0 is x1. That always stays the same. And the only thing that's different between each of these curves is that the damping ratio is changing. And you know from yesterday that as you change the damping ratio from a very large number to a very small number, less than 1, the response becomes from overdamped to underdamped, and then oscillation begins to appear. So logically then you would expect that to be reflected in the phase portrait. And over on the right is the output of the system. So for varying damping ratio, very large damping ratio gives you these exponential shaped curves which kind of react more and more quickly until you get to this kind of purple one on the slide, which in fact is the critically damped case where zeta equals 1. And there's no undershoot or oscillation associated with that, but it has the fastest response time. So equivalently on the left, this is what the phase portraits are doing. You see, they're following a kind of a stable node behavior until we reach this purple one. And once we reduce the damping ratio still further, the oscillation that's seen in the output response, well, that must be captured in the state response because there isn't anything else. Right? The state equations where all the dynamics happen. So then the form of the phase portrait would turn into a stable focus with the swirliness that's involved, and then the kind of oscillation which gets longer and longer is reflected in the number of times we sort of go around the origin before we focus in on that. It's a stable focus. So this transition between a stable node and a stable focus in terms of the phase portrait is equivalent to the transition of the damping ratio from greater than 1 to less than 1. That's the relevant to it. Let's do for amusement purposes only tutorial next, tutorial 5.4. And tutorial 5.4 says we're going to look at 4 separate 2x2 matrices and examine their initial conditions and draw their phase portraits, and then classify each of the phase portraits. Now, unless you're very good, you wouldn't be able to just look at these matrices and tell me exactly what the shapes are. You'd have to calculate the eigenvalues and then work it out. So let's do it in MATLAB. So what I've got is the first matrix is -1, -1 on the top and 1, 0 on the bottom. I'm going to form the state space system, so using the SS command, but we're not interested in the B, C, and D. We're just interested in the initial condition response, which only involves A. So we do initial GSS, give it the initial condition, and I'm going to use an array of initial conditions between -2 and +2 on both x1 and x2 axes. Right? So that's the array of initial starting points, and then we'll just let it go from each of those and build up the phase portrait for this first one. And this is the kind of response that we get. So who would like to classify this response? First of all, is this stable or is it unstable? It's stable, isn't it? Yeah, look at the axes, you can see it's stable. We're going between plus and -2, and it's kind of getting smaller. It's a nice stable. Now, what classification would you put on this? It's a stable focus, exactly. It's got the kind of swirliness that you expect, and therefore, what kind of eigenvalues have we got? Complex and left half plane, right? That's exactly right. Now, in the script, at the bottom, I've got this command here, eig_a. Remember, eig does the same thing as pole. It tells you where the eigenvalues or the poles are. They're the same thing, but it takes the matrix into account rather than the transfer function. And it tells me that our eigenvalues are at -5, that's the real part, plus or minus j, 0.866. So indeed, we have complex conjugate eigenvalues, and they're stable. Let's go to the second of the four matrices. All I have to do is uncomment that. This line here will uncomment, run the script. Who wants to have a go at that? First of all, are we dealing with a stable or an unstable system, do you think? Unstable, isn't it? We've got a 2 by 2 array. You can see that square in there is the array of starting points. But the trajectories, well, they're kind of heading out in a couple of directions here to plus minus 15. How would we classify this, do you think? Saddle point, great. So what's that telling us about eigenvalues? Have somebody over in the back tell us that. One stable, one unstable, and also they're real by the very fact that one is unstable and one is unstable. Exactly right. And if we look into MATLAB and find them, they are at -2, which is the stable one, and +1, which is unstable. So therefore, we have a saddle point in the case of the second matrix. Well, I'm picking the same initial values in all of these. So it's an array of numbers between -2 and +2 in both directions. I mean, you can pick -10 if you want to, but it's not going to change the shape of the phase portrait. The phase portrait is a property of the system matrix, not the starting values. All right, let's go back to the previous case and have a look at it again. So sorry, why have I not? I should have commented that. Excuse me, just bear with me a second. Okay, here's the previous case. The bounds were ±2. Yeah, okay, with you. Well, that's why it's a stable response. Yeah. Okay. Let's move on to the third one. The third one now is this fella. Let's run him and see. So let's begin. Stable or unstable? You can look at the thing, obviously, and it's a stable. Oh, what's the name for that fella? Node, right? It's a stable node, right? Absolutely, stable node, because all these things follow a nice, well-behaved kind of curly thing into a straight line. So it approaches in a straight line from both sides to the equilibrium point, which is called, in this case, a stable node. Therefore, what kind of eigenvalues have we got? Real and stable. You're getting the hang of this now. They're at -2 and -1. You can see that in the screen. And then the final one down here. Let's give that a go and see what we've got. Well, stable or unstable? Unstable. We have to any doubt about that? And it's a what? Unstable focus. Yeah, I would say it's an unstable focus. You can see that it's a bit hard to see unless you kind of zoom in on it, and then I'm going to lose resolution. But there is a kind of swirliness associated with it. So we would suspect that the eigenvalues were in the right half plane and complex. Right? Absolutely, complex conjugates, aren't they? No, they're not. Turns out that it isn't a stable focus after all. Stable node. Yeah, okay, I put my hand up to that one. Perhaps I should have selected the zoom a little bit better. Yeah, okay, yeah. I was fooled too. That's my own tutorial, and that's my own silly fault. Yeah, it is a stable node because it's some kind of a straight line, and they're all heading away from it. on that straight line. Okay, my fault, but we still had fun. Well, I had fun anyway. All right. Now, the last part of this, I want to make the connection between the state space description and the transfer function, and then we're going to stop for a well-earned cup of tea. The state equation can be transformed into the Laplace domain just as if it was an ordinary differential equation, scalar form of differential equation. And this is what you get if you transformed it using the Laplace transform. Now remember, on the left-hand side you had x dot, it was a differential, so you end up with s times x of s minus x0. Remember, when you do a first-order Laplace transform, there's that minus f of 0 that I showed you yesterday appears. So you've got an initial condition point there. And so we've got terms on the left and right involving x of s, and we can take them over onto the left-hand side and say that we have s times I minus a times x of s. So I just haven't included that intermediate step. And take x0 onto the right-hand side. So the right-hand side becomes x0, the initial condition, plus b times u of s. And then what we need to do, we can just multiply through by the inverse of this matrix, s times I minus a. So we've got x of s on the left, that's the quantity we're interested in, that's the solution to this, times x0, plus, again, s times I minus a, the inverse of that, times b times u of s. Now, this matrix, Si minus A, is very important, and you'll see why in just a second. It's called the resolvent of the system, or the characteristic matrix of A. And its determinant is the equation that we needed to define the eigenvalues of the system. And can you see that the determinant of this is going to give us an nth order polynomial in S. Now, you've now got an equation in Laplace, which is the solution to the state equation. You can plug it straight into the algebraic output equation, and it comes out like this, bottom line by 1. And if we make the usual approximation by saying that, well, the initial condition is 0, so we're going to simplify the equation somewhat by getting rid of the first term on the right, and then delete the independent variable, because we know we're talking about Laplace now. Then you have y equals c times the inverse of the resolvent times b plus d, all multiplied by u. And now I've got y on the left and u on the right, so their ratio is the transfer function, isn't it? And that's what we saw yesterday. So y over u is g, and it's equal to c times the inverse of the resolvent times b plus d. Okay? So now what I've got is a matrix equation which represents a transfer function, except now that the term on the left has a dimension. It's no longer just a transfer function, it's an array of transfer functions. It's called a transfer matrix. Each element in that matrix is its own transfer function. Now let's look at the structure of that transfer matrix. The thing is that involved in it is this inverse of the resolvent. This Si minus A is called a resolvent, and it's inverse of that. Now remember how you find the inverse of a matrix. Right, it's the adjoint divided by the determinant, isn't it? So let's look first at the adjoint of the resolvent. Now when you compute the adjoint, do you remember how you can do it? You take each element in the matrix and you delete the row and column that that's in, and then you compute the determinant of what's left, and that becomes your what's called a cofactor. Right? And then plus or minus 1 times that, all transpose becomes the adjoint. It's a little bit involved, but the point is that by deleting the row and column, you're ending up with a polynomial that can't have degree n anymore. The degree has got to be 1 less than that, at most. So each element in the adjoint matrix can't have a degree any greater than n minus 1. You could represent it, if you like, as the sum of powers of S. Each of these E matrices represents the coefficient in each of the polynomials that ends up. But the point is that the adjoint has a degree of n minus 1. But the determinant doesn't. The determinant has a degree of n. So when you form the inverse and you divide the adjoint by the determinant, you're ending up with a matrix which is a matrix of strictly proper transfer functions. It has to be, because when you form the cofactors up here, you lose the order. The order drops by 1. So this resolvent definitely has an order of less, the inverse of the resolvent definitely has an order of n, and it is strictly proper. Every element in that matrix must be strictly proper. So let's plug that back into the original equation and see what happens. So we've got G equals C times the inverse of the resolvent, so the adjoint divided by the determinant. You know that is strictly proper, times B plus D. And bring it all onto the same over the same denominator, and we multiply d by this determinant, you've got c times the adjoint of si minus a times b plus the determinant si minus a times d over that. Now, the significant thing here is this thing has degree n minus 1, c times the adjoint of si minus a times b. That's degree n minus 1. The term on the right, s times a minus I, determinant times d, that has degree n, and this has degree n in the denominator. So, what are the elements of the transfer matrix now, G? The thing is that if D is non-zero, the order of the numerator and the denominator are the same. The elements of G are going to be proper, not strictly proper. Right? M and N will be the same. If D is 0, then this term over on the right disappears, over here. You know that has degree n minus 1, and the denominator is degree n. So the transfer matrix elements must be strictly proper. So you know when you've got a transfer function that is strictly proper, you're going to have a D matrix which is 0, and vice versa, right? When you've got a proper transfer function, same number of poles and zeros, you know you're going to be dealing with a non-zero transmission matrix. That's the difference between them. Most of the time for real models, D will be 0 because the transfer function is strictly proper. That's the difference, and that's why it gets a quad bullet. It's worth hanging on to that point. Oh, well, that point there. See both points. Yeah, that's the other thing that's important too. The thing is that this transfer function here is independent of your choice of states. As I told you before, you have complete freedom to choose exactly what the state elements are, as long as you get the number right. And the point is that whatever elements you choose, once you carry out this transformation to get a transfer matrix, it's always going to be the same transfer matrix, independent of what you've chosen for the state vector. And there it is, I guess. This is the transfer matrix in general terms that you might find. Let's do a quick tutorial, and then we'll break for coffee. Well, we'll do a quiz and then break for coffee, I guess. I'll do the first part of this, 5.1a, because this is the one that refers to the buck converter, and I've been using that, so I'd like to be consistent. We're going to find an equivalent transfer function representation for it, and then verify that the step response is unchanged, and then hopefully the step response will be unchanged, otherwise something's gone dreadfully wrong. So we are in tutorial 5.5. The first part of this we've seen before, so I won't labor it. We're simply creating the state space model. There are the matrices. And then what I'm going to do is to plot the response of the output response of the state space system. I'm sorry, it looks like I'm plotting the states first. All right, there are the two states for this system. Something's gone wrong. Can you just bear with me for a second? That's not what I was expecting for a system which oscillates like a bell. I think this must be the one. This must be the one. I want to stay with the buck converter. So I think this must be the tutorial. I'm sorry I got the wrong one. Maybe I've rewritten them since the PDF was made. This is more like it. This is a second order system, and the numbers look pretty big, meaning the poles are probably a long way to the left, so that when we plot the transfer function, plot the response to this, is probably going to be very, very quick. I think this is the buck converter at this point. Yes, the electrical network. We're good. So let's convert the state space description now into a transfer function form, and you can do that using a script called SS2TF. See, it's a pretty obvious script, really. State space to transfer function, and you just give it the state space matrices A, B, C, and D, which you've just found, or you've got from some other means, and it returns two arrays, which I'm calling num and den. You can guess what they are. They're arrays which are going to contain the coefficients of the transfer function. Now, in order to use those, you need to just plug them into the TF script, as we saw yesterday, because they're arrays of coefficients, and that will produce the transfer function, which will look like this. So it's a nice second-order transfer function with 1, 0. It does at least look like what we've been used to. And then what I'm going to do is plot the response of the state space system and plot the response of the transfer function. Hopefully they'll both be the same. Here's the state space description. It looks awfully familiar. And now when I press run and advance again, hopefully the response will be the same, and it'll be overlaid on this. So with luck, the only thing that's going to change is the color, because they'll be so perfectly matched that you will not see anything different than the color change. It's overlaid itself perfectly onto itself. So this very short demo was just to introduce SS to TF and the fact that it's a faithful representation of the state space model. So let's conclude this thing with a quiz. Who can give me 3 advantages of the state space representation? Man, coffee smells good, doesn't it? Yeah, you can do multiple input, multiple output. Of course, the transfer function matrix would do the same thing for you as well, but I'll give you that because that's how we've written it, represented it today. Computers love it, don't they? Yeah, that's a good one. And the most important one. Yeah, that's the real key one, is that you can represent every system, regardless of its complexity, by the same pair of equations. That's the big one. You could also have said that the theory for discrete time and continuous time systems is the same, but I think we've captured all the ones there. You've got all of them. Can you define the state of the system? Now, what I'm looking for here are those 3 quantities that we need. Right? The first one is the initial condition, x of t0, and we need 2 other things. Oh, don't know all at once. Right, you need the time interval between t and t0, or t0 and t, let's say, that you're going to work, and right,